Every student gets this problem wrong, except for you, because your TA, Andy, and me, we're gonna help you out. So this falls under the category of a composite beam, steel reinforced concrete. And just for comparison, imagine a simpler case where you just had wood and aluminum beams. Since these are made of different materials, you have to convert one into the other one. So we could take the aluminum and convert it into a large amount of wood, or we could take the weaker wood and convert it into a really small amount of equivalent aluminum. Now, concrete has some weird behaviors that are going to make our problem a little bit more complicated, but fundamentally, there's actually a lot in common here, and we're going to be converting our steel into an equivalent amount of concrete, and then analyzing this problem as if it is just one material, concrete. So since this is a bending problem, we start off with the main equation, the Flexure formula. My over I is the allowed stress. And we have to write this twice because it could be the concrete that breaks or it could be the steel that breaks. So they each get their own separate equation. And for the steel, there's an extra term N because we're going to be turning steel into an equivalent amount of concrete. And so this N is going to be that factor, that relationship, which is going to be a ratio of Young's modulus. Basically, how much stronger the steel is than the concrete. So this is going to be the 29,000 over 3,600 is the ratio of Young's modulus. So we've got three things left to find. And M is not the easiest one to do, but let's do it first. M, the bending moment, this is going to be the maximum moment in the beam. We have to find this through shear and moment diagrams, which is going to start off by solving the free body diagram because we have to solve for the reaction forces at the pin joint on the left and the roller joint in the middle. First opportunity for a student mistake on this problem is to not even be able to figure out how to start it. So a lot of students will really struggle since the distributed load has a variable in it. You can't even solve for the force pointing downwards due to the distributed load. You can't get a numerical answer. It's just going to be in terms of W. But that's not a problem. Just keep the W in your answer. So sum of moments about point A, I just have FW times 8. I don't know what that value is going to be. And then F2 times 8. So plug in the numbers here. I get that F2 is 16 W naught. So whatever that value for W ends up being, F2 is going to be 16 times as much. And since FW, the force pointing downwards, is 16 W naught, this means FA is 0. So essentially the ball in the middle, so essentially the roller joint is holding the entire force. And the pin at A is just sort of there for balance because everything, the distributed load is basically perfectly symmetrical over the roller joint. So my shear diagram starts and ends at 0. Just every shear moment diagram starts and ends at 0. It's going to be sloping downwards at a slope of W. Again, we don't know what that value is, but we know it's going downwards at that slope. Right in the middle, it's going to go up 16W. And then the right-hand side keeps sloping downwards because of the distributed load. So moment is the integral of shear. So the area under the curve of shear is equal to the value of moment. So we're going to be concave downwards on moment because it's going to keep getting steeper because the value of shear, V, is equal to the slope of M. So as V keeps getting more and more negative, M is going to be keeping steeper and steeper negative. And so the area of that triangle, that purple triangle, right, area under that curve, the horizontal distance is 8, and the vertical distance is 8W, then 1/2 base times height, we get 32W as the maximum moment. And again, you probably want to pause the video and look back over this shear and moment diagram and the free body diagram, because again, this is the first part where students would mess up because of the value W. If I just put a number in there like 10, then you could actually just go and solve numbers and this would seem 100 times easier. But it's exactly the same, even though it's a W. Just keep the variable in your answer. The fact that you don't have a number is not actually a problem. We're going to go, this is the final answer we're going to at the very end. So at the very end, we're going to be able to solve for what this value W needs to be. So it's super weird to do a sum of moments and get a variable as part of your answer, and then draw shear and moment diagrams where you also don't have actual numbers, you just have variables in the shear and moment diagram. But again, it's gonna work out. It's gonna work out. So we've solved for M, and again, there's gonna be this variable W that we're looking for, right? If W is gonna be the final answer, it has to be somewhere in our equations. We finally got W in the equation, so that's a good thing, not actually a problem. But next, we gotta find Y and I. These are gonna be based on the cross-sectional area. And this is where, if you thought it was already getting weird because we had shear moment diagrams without numbers in them, this is gonna get even more weird. A simply supported beam, like with supports on each end and the beam in the middle, is gonna be on tension on the bottom and compression on top, right, when the beam is bent in a smiley face. A cantilever beam that's supported over on one side, even with a support in the middle, it's gonna be bending downwards and like a frowny face. And when you have a beam bending downwards, the tension is on top and compression is down on the bottom. Concrete does not support load in tension. Concrete can only support load in compression. So wherever the neutral axis ends up being, everything below that is totally fine. It's in compression. We got regular, normal concrete holding load in compression. But above the neutral axis, that's why we have the steel, because all of the concrete that's up there just gets ignored. You have to pretend as if that concrete does not exist. You don't get... Now, concrete can hold some load in tension. It's an exaggeration to say that it holds zero load in tension. That's not technically true, but it's a conservative estimate. We design beams this way to be extra conservative. So we're going to ignore all the concrete up above the neutral axis and only keep the steel. So the steel reinforced concrete, the reason for that steel is to hold all of the tension, because we have to ignore the concrete and assume conservatively that the concrete doesn't hold tension. So the area for the steel, just pi over 4 diameter squared, multiplied by 2 because there's 2 different rods, 0.88 inches squared is the cross-sectional area of the steel. But we have to convert that to an equivalent amount of concrete. Instead of drawing it as just 2 circles, we're just gonna stretch this out and consider it as if it's like a big wide rectangle. And so this extra area is gonna be that factor N. It's a ratio of E over E. How much stronger the steel is versus the amount that is a little bit weaker for concrete. So this steel is gonna function as if it's about 7 inches squared of equivalent concrete. Now, before we can find Y and I, because Y is distance from the neutral axis, and I is going to need parallel axis theorem to the neutral axis, we need to find out where's the neutral axis. It's not necessarily going to be right in the middle. In fact, it's going to be at the centroid of the concrete, but ignoring the top half of concrete. We'll have bottom half of concrete and the steel equivalent of concrete. And we have to balance those 2 pieces against each other. That is where the neutral axis will be. All right, so bottom half of concrete, top half of steel have to balance each other. Area times distance will equal area times distance. So the area equivalent of steel, the 7 inches of equivalent concrete, times the distance, 17.5 minus the neutral axis. That will give the distance from the steel to the neutral axis. The area of the concrete will be the base of 10 times the neutral axis high, because all of the concrete up to the neutral axis is going to be all that's left. So base times height. Now the distance from the center of the concrete up to that neutral axis will be half the height of the neutral axis, y bar over 2. A little bit of math, we get 4.33 inches as the location of the neutral axis. So this is really low. My drawing actually is not very good to scale. It's actually a lot lower than that, pretty close to the bottom. Which means that there's a lot of wasted concrete in this shape. Almost 3/4 of the concrete is sort of wasted being in tension. And so these steel rods are taking place of like 3/4 of the concrete. Last piece of the Flexure formula, I, the area moment of inertia. For rectangular shapes, 1/12 BH cubed, that is for the rectangle, plus AD squared for the parallel axis theorem, because the rectangle is not necessarily rotating about its own center. It's rotating about the neutral axis, right? The entire cross section of the beam is rotating about that neutral axis. The neutral axis is the part that's not rotating. Everything else is rotating around it. So for the concrete, 1/12, base of 10, height of 4.33 cubed, and then AD squared, 10 times 4 for the area. Distance is that 4.33 over 2, so 2.165 squared. Now for the steel, technically we have 2 round rods, but we've converted this into an equivalent rectangle. So my 1/12 BH cubed, 1/12, the height is 0.75. The base, the equivalent base, is going to be my area 7 divided by 0.75. So when I take my base, 0.7 divided by 0.75, multiplied by the height, 0.75, that gives me my area of 7.1. So 1/12 base height cubed. And in fact, this term is going to be negligible anyway. Really, the strength of the steel is not based on the area or it's rotating about itself. It's based on the parallel axis theorem as it rotates about the neutral axis. This area times distance squared. The 7 is the area, and 13.17, this is the 17.5 minus 4.33, that 13 inches squared, that's going to be where almost all of the moment of inertia is from. You can see as I start plugging in numbers, based on that 1/12 BH cubed was 0.33, this AD squared parallel axis term was 1234, right? So you could completely ignore that 1/12 BH cubed for the steel if you wanted to, and you would get to the exact same answer. So final value, area moment of inertia, capital I, 1505 inches to the 4th, right? It's length to the 4th power for units. We finally start plugging in numbers. 4.33 is the maximum distance for the concrete. 13.17 is the value y for steel, because the value y is distance from the neutral axis. Concrete, the maximum distance is just from the neutral axis down to the bottom. For the steel, it's from the neutral axis up to the steel. And then the same 1505 for I on both. So for both the concrete and the steel, rearrange the equation to solve for M, the maximum bending moment before it would break. And I get for the concrete, 1,042 kip inches, and for the steel, 397 kip inches. And now if I go all the way back to my shear moment diagrams from the beginning, that 32W, the maximum bending moment, the peak of that cusp on the moment diagram, 32W was in kip per foot. So let me convert these values. For concrete, I'm now at 86.9 kip feet, and for steel, 33.1 kip feet. Now, since the steel is a lower value than the concrete, that means it will break first. It will break at the lower bending moment. So if we're trying to find the maximum value W, we actually have to use the lowest value M, the one that will break first. So what value of W will get us to 33.1 kip feet bending moment. If the bending moment is 32W, then that means 1.03 kip per foot is the value of W that gets us up to the bending moment that will cause the steel to break first. Full Mechanics and Materials playlist, link down in the description. Good luck on your next test.